It's titled Autonomous Survey in Northern Environments, and the presentation is being given by Rory McKenzie of IIC Technologies. Rory McKenzie is a hydrographic surveyor for IIC, living in Victoria, BC. He has an advanced diploma in marine geomatics from the Nova Scotia Community College and is an avid scuba diver. Are you there, Rory?
Yep. Hello.
Good morning.
Good morning.
So I'm going to hand it off to you, Rory, if you want to share your screen and launch into your presentation. And again, folks, if you've got questions along the way, you can upload them via the chat. Thanks, Rory.
Great. So hello, everyone, and thank you for coming. I'm Rory McKenzie from IIC Technologies, and I'm here today to talk to you about autonomous survey in northern environments. So just as an overview, I'll discuss what the goals of the project were, the survey area, the equipment we used, the mobilization, our day-to-day workflow, the lessons we learned, and potential for future Arctic operations. So the goal of the CHS was to evaluate off-the-shelf autonomous technology in a real working environment and to test the equipment's limitations in a harsh northern place. This survey was more about testing the durability and the safety to extend the survey season, and was not an analysis of cost or efficiency. And in addition, they wanted to successfully complete a survey of a low impact shipping corridor of the world's largest freshwater marine conservation area. So CHS chose IIC Technologies, who partnered with XOCEAN to complete the survey. IIC provided the party chief an on-site crew, data processing, and performed equipment maintenance in the field. XOCEAN provided the XO 450 uncrewed surface vessels, master mariners to pilot them, and online surveyors to collect the data, as well as technicians who provided technical support remotely to the crew on the ground. So the survey area was northern Lake Superior. The depths in the survey area ranged from about 30 to 300 meters, and it consisted of one mandatory and one optional area. And our operations took place between early October and the end of November 2020. So for those who are not familiar with the region, Lake Superior is one of the largest bodies of freshwater on the planet, and the temperatures there drop pretty quickly in the winter. Has an average about 6 degrees in October and drops to around -11 in December. And with an average water temperature of about 10 degrees in October, dropping to 4 degrees in December. So as you can see, it's pretty susceptible to rapid freezing starting in late November, which is around the time of our survey. And it's very famous for its November storms. They've claimed the lives of thousands of people and inspired many songs and stories. During the survey, we observed an average wind speed of about 25 knots at an average sea state of 4 on the Beaufort scale with a maximum of 6. And that's just on the days that we were actually operating and we were out there to observe, not when the conditions were deemed too rough. So as you can see, it's not really a suitable time of year to run a manned survey with a smaller vessel. So we operated at Thunder Bay, Ontario, which is the closest city to the survey site and the largest in the region. Provide us access to stores, contractors, shipping centers, and accommodations. And these are things that would be pretty difficult to come by in remote locations. But the mix of having the harsh environment and the amenities of a large community made this an excellent testing site because we had access to resources should anything go wrong. So the equipment we used were 2 XO 450 uncrewed surface vessels that were both equipped with a Kongsberg EM 2040P multi-beam echo sounder. They're roughly the size of a car and weigh about 750 kilograms. They're powered with a single cylinder diesel generator and coupled with solar panels provide power to 2 electric motors. And they have an operational speed of about 4 knots and can endure up to sea state 6 on the Beaufort scale and generally can survey up to sea state 4. The USVs are equipped with various situational awareness sensors that provide information to the pilots. This includes 360-degree visual light cameras, a rotating thermal imaging camera. This helps during low visibility, as well as radar reflectors, sound signaling devices, and AIS. So the USVs communicate via satellite to a control room, and the vessels are monitored by the pilots for safety, who can intervene if needed, and surveyors can monitor the survey data and set line plans. So our mobilization was actually completed in Lunenburg, Nova Scotia, where XOCEAN has a Canadian office. Local IIC staff were able to meet in a socially distanced setting for a rundown of how the equipment works. And by the time everything arrived in Thunder Bay, IIC staff only had to unload it and perform some quick system checks before putting it in the water. Everything arrived like pre-packaged with all the tools and materials needed, and this allowed for minimal interaction with the public, creating a safer work environment for everyone involved. So our general workflow, the USV would be launched with a light truck at a local ramp, and in the picture you can see me piloting it manually through the harbor. This was done just as an extra precaution when moving through the high traffic area. And once the USV had cleared the breakwater, operators in Europe would assume control and begin transit to the survey site. The units would survey fully autonomously, following pre-programmed survey lines. And the course would be automatically adjusted using the new QPS Quincy Autowash function. As you can see in the photo, the paths are based on the desired overlap, and the unit would adjust accordingly. This minimized the occurrence of any gaps between lines. And SVP casts were performed using an auto winch at the surveyor's discretion. The USV would be deployed for roughly a week or until the weather had become too rough to operate. Sometimes the USV would just navigate to a sheltered bay and hold position until the weather had cleared. However, this left the USV exposed and no one would be able to get it to something go wrong or weather get even worse than predicted, which when operating in Thunder Bay is a pretty common occurrence. If you're expecting the night to be one thing, next thing you know, it's 10 knots higher than that. So once we would get it on shore, the data would be downloaded and any maintenance needed, such as oil changes, would be performed. And then the vessel would be relaunched as soon as possible. And once the unit was underway, the on-site crew member would process and QC the data and then get it ready to be shipped back to the main office for finalization. We learned 3 main lessons during operations that we believe relate to working in the North with an autonomous vessel. The first one is that there are logistical advantages and limitations that need to be considered when it comes to USV transportation. 2, it's very important that you have the capabilities to perform maintenance and repairs in the field. And 3, you must consider the effects of freezing spray on your equipment. So first, transportation by road. So the USV's small size makes pulling it out of the water and relaunching it pretty quick and easy compared to a small survey vessel. And when working in a remote location, the closest boat launch may be very far from sections of your survey block or not exist at all. However, with the USV and a light truck, you can take advantage of the lower quality and potentially even private boat ramps that are not intended for commercial use. And this could allow for rapid mobilization and minimize transit time. So the map seen above was made after we consulted with local mariners, and it shows all the possible boat launches that could have been used to launch the USV. And we even developed a weather strategy where, depending on the prevailing winds and such, we determine what the most efficient launch and recovery site is from. And this is something we really wish we had taken more advantage of during our operations, but it did help us a few times when having to escape certain weather systems. So transportation by chase boat. So the requirement to have a chase boat for us created a limiting factor. The point of the chase boat was to ensure that the unit would not be stranded for long, potentially drifting into rocks or across the American border should something go wrong. And our survey was actually ended because the conditions became too dangerous for the manned crew to assist the USV and not for the USV to continue operations. All parties agreed to end the survey when the cost of hiring a large chase boat became too high the frequency of the storms was increasing, and local mariners were not eager to be on the water to assist a non-crewed vessel. And this was very justifiable, considering that by this time of year, the Coast Guard had removed all their vessels for the season, and there were almost no one else in the water available to help us. And so we believe that having a larger vessel double as a survey vessel and the chase boat would have been more practical as we got later into the season. So field repairs. So it's important to remember that machines need maintenance, and no matter what you do, things will break eventually. Maintenance and repairs were straightforward and successfully completed by a field crew with very limited mechanical experience. However, in remote areas, you have limited access to part suppliers, unlike Thunder Bay, which we had access to several distributors and mechanics who could provide advice if needed. When we needed anything we couldn't find, delivery time became our biggest problem, especially due to the increased delays caused by the pandemic. And the further north you go, the more of a problem that will be with or without the pandemic. It's more realistic to have a spare USV or parts standing by in storage on site than it is to have a spare boat ready to go. And it's more pragmatic than waiting around for a week for a part to arrive. And also, you need a good workspace. When the unit needed any maintenance, we had a warm garage, and XOCEAN technicians were able to guide us over the phone through the whole process. However, a proper workstation like this might be more difficult to source in remote communities, and no one wants to be performing that maintenance outside in sub-zero temperatures or during a snowstorm. Access to such facilities would have to be planned well in advance. So freezing spray. It's very common for ice buildup on the Great Lakes. Mariners are often required to break that ice on a regular basis, and failure to do so can cause the vessel to become unstable, especially when you're running long lines in one direction where the ice tends to build up on just one side. We were concerned that the USV would be impacted in a similar way, but unlike the manned vessel, there's no one there to break the ice off. However, ice buildup did not actually impact the stability of this USV at all. This is likely because of the unit's low in the water design and its large flat black deck, which allowed for the heat from the warmer lake water and the heat from the sun to limit any freezing. And as you can see in the photo, the gantry is the most susceptible to freezing, but it has such a low surface area that the ice didn't have much opportunity to aggregate, and therefore had minimal impact on the maneuverability or stability of the vessel. Unfortunately, we did have one problem where ice buildup blocked the air intake on one of the units, resulting in the generator getting starved for oxygen. But this only impacted one of the units because it had a slightly different design than the others, which had a lower additional air intake. And this was quickly remedied with a modification in the field by placing another air intake closer to the waterline where ice would not have had the opportunity to build up. And that can be seen in the photo. We think that there's a potential use in the future of hydrophobic sprays and coatings similar to what you see on aircraft that could help mitigate ice buildup for long deployments. So future work. We believe the best way to utilize this technology in the Arctic is as a force multiplier. And this is based on the limitations of a chase boat, the need for a secure, warm place to perform maintenance, as well as store spare parts. And we believe operating multiple USVs in conjunction with a large mothership makes the most sense. And this method has already been shown using the Dolphin semi-submersible ASV back in the early 90s. They were able to successfully complete a survey operating in -20°C with 30 to 40 knots of wind and freezing spray off the coast of Newfoundland. And they found it had greatly increased their data collection efficiency, which is essential considering how short the Arctic survey season is. However, they had a specially designed launch and recovery system that worked in rough seas, and this would have to be something that had to be developed to see similar results. So as sea ice retreats and interest in the region will grow, creating a greater need for reliable charts, the region will see more shipping, resource extraction, and tourism. And Canada will need to increase its presence and exploration of the area for both safety of life at sea, as well as asserting sovereignty. With a low population density and limited infrastructure, this is going to be a difficult task. Autonomous technology could become a great tool to increase presence in the region and collect the data needed for managing and protecting Canada's Arctic waters. Thank you for coming.
Great, thanks, Rory. That was yeah, very, very interesting. Again, coming from a company that manufactures USVs, you know, I found that very, very informative. I mean, that looked great, and as usual, ice is the issue.
Yeah,
especially working up in the north. But looks like the design of those vessels, you know, really mitigated that the ice buildup. So that's great.
Yeah, I agree.